Okay, so I'm gonna get started in the interest of time. Good morning, everyone. Welcome to this unusual time for our seminar. So I'm really pleased to introduce our seminar speaker today, who is Dr. Erkin Ötleş, not a fake doctor like myself, a real doctor, Dr. Ötleş. Okay, so Dr. Ötleş is actually no stranger to us. He's one of our own. He received his bachelor's and master's degree in this department, so I'm sure you took lessons in this room maybe, okay. And then he took an interesting, adventure. So he went to Michigan and he got a dual degree, an MD and PhD degree. MD degree and PhD was in industrial and operations engineering. And now he is back to Madison. He is doing his residency at the emergency medicine department at UW Medical School. And he has some interesting things to share with us. So please join me to welcome Dr. Ötleş. Thank you.
Thank you very much, Dr. Ötleş. All right, I just turned on the mic. Can you guys hear me okay? And I'm someone that likes to roam a little bit, so hopefully you guys don't mind me tracking a little bit, but if I get distracting, just tell me to come back up to the little castle you guys have set up. So today's talk is going to be under the general theme of machine learning for healthcare. And I'm going to be talking about a series of projects that I did across the model development and implementation lifecycle, specifically looking at longitudinal settings or doing stuff over time in medicine. And Dr. Ötleş introduced myself, so I'm not going to necessarily belabor things, but I was trained by Jenna Wiens in computer science at Michigan, and then Brian Denton in industrial and operations engineering. I also worked as a healthcare data science manager and was an engineer at Epic for a little while. All of that sort of informs my perspective on using data effectively to make decisions as a physician or as a health system. So my perspective is that we're sort of in a world where there's three big Ps, in my world at least. There's the patient, the physician, and the prediction. And we need to sort of figure out the nice sweet spot where we can get all of these things to work together, ideally so we can advance the health of the patients that we're caring for as physicians. I'm particularly interested in making computational approaches so that we can have AI tools being very useful for physicians and health systems in serving patients. And I think this is a particularly fruitful area in terms of research, which I'll get into for the majority of this talk, but also in terms of funding and teaching. And I'll actually touch on those very briefly at the beginning of the talk, and then we'll jump into my research. So I think healthcare AI funding, the landscape right now is like a little bit uncertain in general, but a diversified approach is probably the best approach. And I think this is an area that many different funders would be interested in funding sort of full-heartedly. And let me see if I can not have my computer turn off on you guys. Go into sleep mode. I apologize about that. I think that there are traditional funders like NSF, AHRQ. Those are people that would probably still be interested in doing this. It's just maybe a question of what their budgets look like. But I think they're going to be a big component of my work going forward. I also think that there are medical associations, people like the AAFP or the American Association of Family Physicians, who I've worked with in the past and have actually funded small grants of mine in terms of innovation. And then there are philanthropic organizations like the Gordon and Betty Moore Foundation who are actively investing in healthcare AI. And then you have industry partners. Some of my work was actually funded by an industry partner, Peers Health, essentially an insurance agency that paid to do some of this work, and I'll talk about it briefly in a little bit. My presentation, let's see if I can keep going. In terms of teaching, I think that there's a sort of a panoply of different people that need to be educated on healthcare AI. I think from the undergraduate level, we have sort of the basics of health systems engineering. That's something I'm very confident in teaching. I also think that there's advanced techniques in terms of AI for healthcare that we can start to teach about. And then there's sort of the basics of AI, ML, data science, sort of irrespective of healthcare as well, that are all sort of well within my wheelhouse for teaching. teaching. And then there's the mentorship of graduate students and medical student trainees. And then we can think about even further up in the life cycle, we have practicing physicians, healthcare executives. All of these people will need to be eventually upskilled in terms of how do we use artificial intelligence effectively in healthcare. So now moving a little bit more towards into my actual research focus, a lot of these projects are going to be from my dissertation, which the title's up here, but the focus is on longitudinal settings. And why do we care about time? Why do we care about longitudinal settings? Well, time plays a crucial role in everyone's lives, but it's particularly crucial in the practice of medicine. So let's say you go and see your doctor. They're probably going to ask about the onset and time course of your symptoms. If you have a symptom, they're going to want to know when did it start and how has it changed over time. And that's because the temporal ordering of symptoms and other diagnostic information actually impacts the likelihood of you having different types of diseases. So if you had a cough a couple of weeks ago and now you're having shortness of breath, well, it's more likely that you have atypical pneumonia than something else because maybe you had a viral process and then now you've had a pneumonia that had time to settle in. But when you zoom out from individual patient interactions to the healthcare system, you can actually see that time impacts our healthcare system as well. So over time, our populations are going to change. We get new diagnostic and therapeutic modalities. We also implement new workflows. And we also start to see new diseases arise, right? And you can think of some of these things as like potentially slow evolutions, but just think back a couple years ago. The pandemic is an incredibly salient example of a massive, abrupt change in our healthcare system. So what does this mean for people that are interested in applying machine learning to healthcare? Well, time is an important factor for the practice of medicine. So thus, it should be considered as an important factor for those of us interested in applying machine learning to healthcare. So there are two big areas where we can consider time. One is model development, and the second one is model implementation. Development is the actual creation of models, and this involves the selection of predictive tasks, collecting and preparing data, and conducting model training. But the longitudinal nature of medicine can complicate this. For example, how do you best incorporate complicated temporal patient data into your model? And then implementation is the actual integration of models into care. This involves connecting models to health IT systems, assessing their prospective performance, and designing clinical workflows that take advantage of the model predictions. Model developers should ideally monitor model performance over time, and they may want the opportunity to improve models and their associated workflows over time as well. So ultimately, implementation involves making predictions in real time, and thus it exposes the models to changes that are occurring in the healthcare system over time. So this leads to the central thesis of the work I'm going to be going through, which is that the longitudinal nature of healthcare, understanding that is key to actually making better models and then having them work well during their implementation. So we're going to discuss several different projects that share this longitudinal focus. And they're going to span across both development and implementation. We'll spend the majority of the talk talking through three projects. The first project focuses on the development of models. And this one, my primary contribution is to assess the value of observations collected over time for return to work prediction. This work was published in the Journal of the American Medical Informatics Association. It's also covered by a US patent that was recently awarded in January. Chapters 3 and 4 focus on implementation. In Project Project B, we discussed the changes to model performance that occur after model implementation. And this work was published in 2021 at the Machine Learning Healthcare Conference. And then Project CI introduced a new rank-based compatibility measure for risk stratification model updating. And I also develop approaches to optimize models for this compatibility measure. And that's actually where we'll spend the majority of this talk. I'll give a brief overview of Project A and Project B, and then we'll spend the majority of the time talking sort of at length and in depth about Project C. So let's dive into Project A. So this project focuses on occupational injuries. Occupational health professionals, so case managers or nurses that manage many people that got injured at work, they use return-to-work prediction models. And these models help them to make better decisions in terms of treatment and staffing. So which case managers are going to be assigned to take care of a case, and which ones are going to have certain resources allocated to them. And currently, the return-to-work models that we have in this space actually ignore all longitudinal observations. They only use the information that was collected at the time of injury. For example, they'll use demographic and injury information in order to pass to a model, and then that model will then say, I think this patient's going to return to work in 55 days or so. So what we actually sought to do is say, well, we have a whole bunch of longitudinal information that we think we're leaving on the table in terms of value. Can we increase the predictive performance of models if we do include longitudinal observations? Specifically, compared to only using the information from around the time of injury, do we observe performance improvements with models that utilize longitudinal data? And we hypothesized that longitudinal data observations improve prospective performance, and that's because we've seen it in other fields as well. So peers gave us access to a large retrospective data set of a couple million patients, and we trained a model that uses all these longitudinal observations, and we compared it to a baseline model. I'm not going to have time to actually go through this model, but there's a couple things that are interesting that I'll highlight. This model actually functions sort of similar to a large language model in that it takes observations over time and converts them to tokens. And it presents the model with a series of tokens that represent observations over time. And the model's able to learn the representation or meaning of diagnoses and treatments. And it'll learn them as a part of the general learning process for the model as well. Yeah. So it's a treatment outpatient primarily, because these are folks that are injured on the job, and they may have a hospitalization, but many times, like the vast majority of the data set, it's actually people that are out in the community. They're just not able to go and work, but they're getting most of their care in the clinic as outpatients. Yeah. So a lot of my work does focus on in the hospital stuff, though, but this is more of an outpatient-focused one. So we assess the daily predictive performance of models in terms of both discrimination and calibration. In terms of discrimination, the model that we made outperforms the baseline model, and it has a significant increase in AUROC. Also, it has a better expected calibration error than the baseline model that is currently used by industry. So the big takeaway from this work is that return-to-work prediction modeling can actually significantly be benefited by using the longitudinal observation information. And additionally, some of the stuff that's buried in this work that I'd like to eventually highlight more of is some of the techniques that we have to build longitudinal models in an automated fashion, because there's a whole package of stuff that I built for this that's sort of in the supplemental that hasn't really been seen the light of day. So that's something that I'd like to eventually expand upon a little bit. So now we'll move from a quick tour of that first project into Project B, and we're going to be going from model development into implementation. And so Project B, we focus on understanding the prospective performance gap. And so the prospective performance gap is something that I think many of us are familiar with, but I'll basically define it very quickly for us. So this gap actually quantifies the difference in model performance between an a priori estimation and the actual prospective performance of a model. So machine learning models are routinely developed and validated using retrospectively collected data. And then they are prospectively implemented, right? So for example, let's say we go back in time when I have maybe a little bit less gray hair. We might use data from before 2023 to develop a model, right? And then we could take data from 2024 and we could validate that model and say, okay, we think it's going to work about at this level in terms of AUROC, in terms of accuracy, in terms of expected calibration error. And then we would go about starting to use it in 2023. However, estimation that we have from 2024 is just an a priori estimate, right? We don't actually know how well it's going to start working in 2025. And so it may actually start to perform slightly worse in 2025. And we've actually observed this with many different machine learning models that are used in healthcare. When you start to use it, we have slightly worse performance than expected. And this prospective performance gap is often attributed to changes in care processes and patient populations. For example, a large shift in medical practice could affect model performance, right? If we start doing a new test that the model doesn't know about, that's information that is no longer flowing to the model and thus may not be incorporated in the predictions it's making. And so thus the temporal shift is generally expected to lead to a decrease in the overall model performance. And that's because the data tends to drift away from the model that were originally used to create the model. However, there's also differences in IT infrastructure that can affect the prospective performance gap. And that's because the infrastructure used to develop the models often significantly differs from the infrastructure that is used to serve the model in real time. For example, the retrospective infrastructure may backdate information, like nursing vitals, to the time of observation. So you'd expect when you're using the model in real time, it wouldn't actually see the vitals that were charted at that time because they're not going to be entered into the system until the nurse actually enters them. But if you look in the database, it says nursing vitals from noon were normal. However, in the real-time database, those won't be entered into the computer system until the nurse actually has a moment to sit down, which is going to be 4:30 p.m. And this will impact the model as it runs prospectively. So there are two key differences between retrospective and prospective validation. That's time and infrastructure. Using held-out validation data from the most recent year seeks to mimic the temporal shift, but it doesn't account for the infrastructure shift. And as the data are still retrospective in the sense that they've been accrued from the retrospective infrastructure. So in practice, we expect to observe a prospective performance gap that's also influenced by infrastructure differences as well. So then we ask, what are the causes of the prospective performance gap? More specifically, what are the temporal and infrastructure shifts that contribute to the prospective performance gap? And then we hypothesize that the infrastructure differences will be an important component to this. And in order to answer this question, we conducted a study where we used a hospital-acquired C. difficile infection risk prediction model that was implemented prospectively. And it was also retrospectively validated. And we did a careful analysis across these in order to tease apart the two different sources of shift. So the model was retrospectively validated in data collected from 2019, and then we prospectively validated it in 2020. And we were able to evaluate it in terms of discriminative performance. And by essentially pulling data from the different systems at different times, we can disentangle the two different components of dataset shift, temporal and infrastructure shift. In 2019, the model had an AUROC of 0.778. Prospectively, in 2020, it actually decreased slightly. And this is around the time that COVID hit our health system. So it went down to 0.676. So that's a performance gap or a decrease in performance that we have displayed up here. However, the gap is not entirely due to patient populations or clinical workflows, because when we calculate out the temporal shift, that is, the differences due to the change in population or workflow over time, we actually saw that the task got slightly easier in 2020 relative to 2019. In contrast, the infrastructure shift was positive and actually drove the majority of the whole performance gap. So what this means is that infrastructure is actually driving our degradation for the performance of this model. And when most researchers focus on temporal shift, attempting to build models that are robust to distributional shifts, we're actually ignoring another set of potential degradations that can occur to our model, right? So it's notable that we had this infrastructure shift being the primary contributor to our model's performance degradation. So in this work, we identified the two main sources of infrastructure inconsistencies as well. First, we found that the discrepancies were due to some of the ways that information flow from the EHR into our retrospective data. And we developed debugging methods that we discuss more in the paper that's published. And then we also found that some of these structures of inconsistencies are pernicious, and it's actually just due to the way that our fundamental fundamental information systems work. So the way that the EHR works is inherently dynamic and will overwrite some of the data that are passed into it. And so it's very hard if you have a retrospective database to be able to tell what the data looked like at a certain time. And so that's very problematic for a model developer who's interested in saying, I'm going to use this model prospectively, and I'm going to expect that the data are going to look like this in a certain time point, because you have no traceability for that. So this means that when we are taking snapshots of data at different times for development and validation, we have a problem, and we need to develop methods in order to overcome these. And some of the methods that we have in the paper allow us to start to overcome it, but it's not enough yet. We actually need to develop new methods and new ways to collect data and build models in order to overcome infrastructure shift. And I think this is a pernicious, difficult problem, but before we can even do it, we had to recognize that it was an issue, and that's sort of what this work does. So now we'll switch.
Do you want questions?
I can take questions anytime, yeah.
I was just curious about, like, when you say we demonstrated infrastructure effect, what do you mean by demonstration? Like, is it like through a numerical experiment?
Yeah.
Okay, so you picked up different times.
So in the slides don't go in enough detail to fully sort of explain it, but sort of the summary of it is we had this model that we ran prospectively that we implemented, the C. difficile risk infection prediction model. And what we did is we were able to pull data from its prospective performance and then also pull data retrospectively. And then we were able to run the model on the different sets of data for different time periods. And by doing that carefully for different time periods and the different infrastructures, you can actually compare across the same time period different infrastructure, isolate infrastructure difference alone, and you can also do across time, and so you can get time alone, and you basically decompose the two sources of shift, and then you see infrastructure is actually a big deal. Let me see if I can get my clicker to work real quick, and this will untether me a little bit. It doesn't look, it's not going to work, so we'll just continue. So now we're going to go into the third project, which focuses on updating models that are in use by physicians. So I view physicians and models as functioning as teams. For example, you can imagine that we have a set of hospitalized patients, and we would like to evaluate them for a deterioration risk using the expertise of a physician and a model together. The physician might have a good sense of which of these patients are at risk, those are in red, and which of them are not at risk for a certain outcome, and those are in green. And maybe they haven't encountered some of the data from some of the patients, or they don't know enough about some of them, so they're not entirely sure about the ones that are in gray. Simultaneously, a model might assess the patients as well. And it might have access to EHR data that the physician isn't actively thinking about. So it might have different assessments than the physician does. So ideally, there's information sharing that occurs primarily from the model to the physician, but in some cases, you could think about it going the other way as well. And then the physician model team is going to be able to assess the whole patient population a little bit better than either one could individually. So that's a great goal, having physician and model work together as a team, but it's complicated because we ideally need to update our models over time. And when you do updating, you're going to run into problems, which we'll get into in a moment. But you might think about, like, well, why do we need to update models over time? And this may be obvious to an engineering audience, but less so to a physician audience, so I'll go over it sort of briefly. One is that model performance tends to decrease over time, like we've discussed previously. The second one is that there may be abrupt changes to infrastructure. For example, an EHR upgrade may fundamentally change important model inputs. So models may not work very well after that update, and I've seen that happen. The third one is that, and usually it's the this is the one that people are sort of thinking about, is that we have new data that we've collected, and given that we have more data, we can make a bigger and better model. And you can say, okay, well, that sounds good. Let's always be updating. However, the issue is that model updates can mess with the user's expectations. And so here's a personal example from my life, right? I use Siri to set a timer, and I'm grilling stuff, and my hands are dirty, and I say, hey, Siri, please set a timer for 5 minutes. And then usually Siri responds and says, okay, done, and then I have my timer going. But sometimes my phone updates, and for whatever reason, Siri behaves a little bit weird, and I have my request, and I say, go ahead and set the timer. But then Siri responds with, oh, actually, you don't have a timer application set. And so my hands are messy, and I'm trying to not burn stuff on the grill. But for whatever reason, the update messed with my team performance between me and Siri. So you don't want this happening in high consequence domains like medicine, right? You don't want user expectations to be subverted. So if you have a physician that was using a model and they thought the model was working well, you would be very happy, and the team performance would be pretty good. But what happens if you get an updated model? Well, what could happen is that potentially the performance of the model works slightly better, but the ordering of the patients, if it's a risk stratification model, that may change a little bit, and the physician may not be expecting that. So then the team performance may decrease because the physician's expectations are subverted. And that's sort of an extreme example, but you can think about other cases where we might have a model that is better in terms of performance, but the team performance can degrade. And this has actually been empirically shown by Bansal et al. And this is a sort of a schematic of their findings. What they did in a real user study is essentially had users using a model, and then they switched the model over at a certain time point into 2 different models. And they found that certain models led to performance degradation, that's in red, and those are models that mess with the user's expectations. Whereas if they had a model that had sort of consistent behavior with the previous model, that would not necessarily lead to a team degradation in terms of the team's performance. And they had the same overall model performance, but the way that the user's expectations of the model's performance differed. And so you can think about, you would want to avoid the red case for model updating in healthcare. So this starts to introduce the notion of compatibility. And compatibility is a measure that quantifies how much an updated model continues to produce the correct behavior exhibited by an original model. Thus, it's a measure to actually assess the perturbation of a user's expectations of a model. So a potential goal when updating models would be to have very high levels of compatibility because it's going to lead to better team performance. So you may want to select that green model over the red model when you're doing updating. But let's now discuss how you would potentially assess compatibility. We have an original model up here, and we also have a patient. We can use the model to assess the patient. And we can see that this model, the original model, correctly assessed that patient. Now we can consider updating this model. We can assess the compatibility by using the same patient on the updated model. If its behavior exactly matches the output of the original model, then we would say it's a compatible model. If we have a different updated model, and let's say the different updated model gives us a different answer than the original model, we'd say that this new model is incompatible. So a user accustomed to the original model would be unpleasantly surprised by using this new rightmost model. This is something that we would like to avoid in order to foster user trust. So we'll use these ideas that were introduced by Bansal et al. To talk about backwards trust compatibility, which is a measure that they introduced. And what we'll do is we'll walk through it very briefly in order to motivate my work. And this measure is called CBT, or backwards trust compatibility. It's the chance that the updated model's labels are correct, given that the original model's labels were correct. So here's the CBT equation that's written out in English. and it takes the original and updated model and compares the labels that they produce. In the numerator, we assess both when both models are correct at the same time. In the denominator, we assess only if the original model was correct. Thus, it allows us to calculate the given portion of the probability. Ultimately, it yields a value between 0 and 1. If CBT yields a value of 1, this means that the updated model is perfectly compatible. If it's 0, then the updated model is perfectly incompatible, which means it produces wrong labels for every patient the original model labeled correctly. This measure is ideal for assessing compatibility when updating models that are classification models. However, there are some problems when we start to look at this compatibility measure for use in healthcare, because it depends on a strict equality comparison of the model's labels. Thus, it's not well suited for use with risk stratification models, which are the models that we tend to use most in medicine. And risk stratification models, they produce continuous values, right, between 0 and 1 in order to rank patients by risk. To use CBT with a risk stratification model, we would need to employ a decision threshold. For example, we could set a threshold arbitrarily of 0.5. This would round all patients to either 1 or 0. And then we could use CBT for risk stratification models. But this is pretty problematic for use in healthcare. For example, one issue is that you may have several thresholds in use, right? Dr. A may be very conservative and wants to make sure that they're catching everyone that might be at risk. Dr. C may only be interested in only the highest risk patients. So, just from physician preference, you don't necessarily know which threshold you'd want to set. Additionally, you might not even need a decision threshold, or you don't want that. You may use a model based on the state of your system. You might be interested in a system that's only going to select the top X patients, where X is determined by the number of beds you have available in your ICU, in which case a threshold doesn't really make any sense. You want to make sure that your ordered list, where the top patients are the sickest patients, are actually the sickest patients. So in this case, we wouldn't want that threshold at all. Furthermore, we generally seek to maximize the correct ranking of patients when developing risk stratification models, and we generally use the AUROC measure for this. And unfortunately, CBT has no direct relationship to AUROC. This means you can't actually directly assess any trade-offs between compatibility and performance. So I set out to address some of these gaps. The first thing I did was define a new rank-based compatibility measure, which we'll call CR. I then characterized this measure and its relationship to CR, and I introduced new methods to create updated models with very high levels of CR. So this is our problem setup, if you will. We would like to evaluate the compatibility of updated risk stratification models without setting any decision thresholds. The AUROC serves as inspiration for our new rank-based compatibility measure. It measures the proportion of patient pairs that correctly are ranked by a model. So this is the equation for AUROC. It's going to take it takes a single model at this point. It counts the number of patient pairs that are correctly ordered in the numerator, and it normalizes by the total number of patient pairs. The numerator operates by comparing the risk estimates generated by the model, and if the risk estimates are correctly ordered, the pairing is counted as correct. The AUROC can be thought of as a probability that the model correctly ranks a patient pair. Thus, it's a value between 0 and 1, 1 perfect ranking for all patient pairs, 0 incorrect ranking for all patient pairs, 0.5 is essentially random. AUROC doesn't use a threshold, and it's our go-to measure for assessing machine learning model discriminative performance in medicine, specifically for risk stratification models. So back to our primary problem, we want a rank-based compatibility measure. This is a measure that's going to inherit from both CBT and AUROC. It's going to inherit its general structure from CBT, with the numerator assessing the correct behavior of both models, and the denominator normalizing based on the correct behavior of the original model. So we'll use the AUROC as inspiration to redefine the notion of correct behavior, using the ranking of patient pairs in lieu of a strict equality employed by CBT. So the rank-based compatibility measure, CR, measures the chance that the updated model correctly ranks a patient pair, given that the original model correctly ranked that patient pair. So here's the formal definition of CR. Let me take a break and we'll walk through it sort of step by step. It's going to take an original and an updated model, and it's going to function by comparing their risk estimate rankings. Highlighted in blue, we have the assessment of the original model. If the original model correctly ranks a patient pair, then the function in blue is going to be 1. Otherwise, it'll be 0. This evaluates if the original model's rankings were correct. Highlighted in yellow, we have the assessment of the updated model. It's very similar to what we have in blue. If the updated model correctly ranks the patient pair, then it's going to be 1, otherwise 0. Thus, the yellow expression tells us if the updated model rankings were correct. So now we can assess if both models were correct at the same time for the same patient pair. We'll do this by multiplying those two indicator functions together. That's the numerator. And then we do this assessment over all patient pairs. And ultimately, this will yield a value between 0 and 1, which can be thought of as the probability that the updated model correctly ranks a patient pair, given that the original model correctly ranked that patient pair. So if CR yields a value of 1, this means that the updated model is perfectly compatible in terms of ranking. If it's 0, it means it's perfectly incompatible. So it produces incorrect rankings for every single patient pair the original model correctly did. So to quickly recap, CR is a new rank-based compatibility measure. It's inspired by AUROC. It's not threshold dependent, overcomes some of the limitations by the previously proposed measure. We go further and we sort of characterize this measure. We show it has a direct relationship with AUROC of both models. We won't go into that in this talk. That's sort of in the MLHC paper. And we show that there's like a lower bound where CR is supposed to essentially increase as model performance increases as well. Now, if we have this model, we have some questions. The first question is, do we get rank-based compatibility for free when we update models in the traditional way or when we target AUROC? And more specifically, you can say, like, if we have a measure of CR for new models, are we going to get very, very close to 1 when we train an updated model that uses binary cross-entropy loss, or the standard approaches to creating an updated model? And our hypothesis is no, and that's based on some analytical reasoning that's discussed in the paper. But basically, there are many ways to create a new model that would have high performance in terms of AUROC, but they're not guaranteed to necessarily have high compatibility with the original model as well. In order to empirically answer this question, we created an experiment using the MIMIC3 mortality data set. And this is a publicly available healthcare data set from Beth Israel Deaconess Medical Center. It's pre-processed. We pre-processed data from this data set using a package known as FIDDLE, and we essentially build a model that does 48-hour in-hospital mortality prediction. And we split this data set into 3 partitions. One data set's used only for the original model creation. The second data set is used to create updated models. We create 150 different candidate update models. We train them using binary cross-entropy loss. And then we have some variation induced by data set resampling and varying the regularization rate. And then we go about selecting which of these models may be the best. And then we have a third data set that's held out from both model development data sets. And we use this to calculate the original and updated model performance with this evaluation data set. And we additionally calculate the CR between the original and updated models as well. And there's a large discrepancy in size of data sets, if you may note, between the original and updated models. And that's because we wanted to intentionally simulate when you go about making a new model, usually you have much more data to do that updated model. So we conducted about 40 replications of this experiment. The blue dots represent the AUROC of the original models, and these tend to range between 0.75 and 0.8 for the original models. Now we plot the AUROC of the updated models, And there's 150 models for each of these replications. And so we present the mean and 95% confidence intervals for these updated models. And we see that the updated models have improved AUROCs compared to the original models, which is expected because they're presented with more data. And then we now present the CR, the compatibility for these updated models. And so for each of the replications, we have the CR in gray here. I can observe that this range is limited sort of between 0.5 and 0.95. So if you want a model with incredibly high levels of compatibility, above 0.96, it'd be unlikely to occur sort of naturally with standard updating approaches. So when we reflect on our first question, we see we don't totally get CR for free. And that's because the CR's range that we see, it's sort of in a limited band, and it doesn't go all the way up to 1, which is in line with sort of our analytical thinking about this. And so it motivates some of our techniques to think about, like, well, how would you go about building a model that has a higher level of CR? And that's what we're going to touch on briefly next. So when you go about making a model, you generally, for these risk stratification models, you may use something like a binary cross-entropy loss, and we use that to train updated models. So this loss helps to create models with high levels of AUROC because it forces models to produce lower risk estimates for 0 labeled patients and higher risk estimates for 1 labeled patients. And the main thing to note here is that it doesn't have a direct focus on ensuring any type of relationship between an original and updated model. It's totally besides the point of this loss function. So we have an opportunity here to make a new loss function that builds on rank-based compatibility. And we'll introduce it. It's fairly straightforward. This rank-based incompatibility loss is essentially just 1 minus CR, because we can just take that measure and convert it into a loss function. So minimizing LR will lead to higher levels of compatibility. And we actually have a differentiable approximation of this in order to use stochastic gradient descent. And we denote that with the tilde. I won't actually go into some of the tricks there, but you can relatively easily approximate it with sigmoid functions and such. So now you can think about, well, you might want to balance the existing approach of binary cross-entropy loss with this new loss function. So you can do sort of a weighted loss function where you take binary cross-entropy and you weight it against LR, and you can control the trade-off with the parameter alpha. When alpha is 1, you say we minimize binary cross-entropy loss. When alpha is 0, we minimize the rank-based incompatibility loss. And if you set it to 0.5, you're going to sort of try to do both equally. Now we have a second question. Can we make updated models with higher levels of compatibility with this? Specifically, when compared to standard update model generation, can we use this weighted loss function to generate updates with better CR? And our hypothesis is that this weighted loss function will produce better models in terms of CR. But the related and more important question is, like, what happens to our AUROC performance when we do this? So we can extend the original experimental setup, and the main modification comes in the creation of updated models. We produce the same original models, and we create 150 updated models using binary cross-entropy loss. We refer to these as the selection models. They're denoted in the gray side. We also have optimization models, and they use this weighted loss. And they have various rainbow colors representing the alpha value that we're setting to. And we basically train a model for each of the alpha values. After updated model training, we compare the selection models against the optimization models. We pick the selection model with the best validation AUROC, and we compare the selection model to the optimization models in terms of AUROC and CR. These are calculated on the held-out evaluation data set. So now let's look at the performance results. In these graphs, we'll have the performance on the vertical axis versus alpha. And the x-axis represents alpha. And that's essentially what threshold we're setting for the optimization models. So let's look at CR first as our initial performance measure. So each of the bar graphs here represents an optimization model in rainbow colors against a selection model in gray. And these are 95% confidence intervals across the 40 replications. On the far left, we see alpha set to 0. So the purple bar there represents the optimization model that's entirely focused on compatibility. So we're going to naturally see a big difference when compared to the selection model. As alpha increases, though, we increase our weight on binary cross-entropy loss. Thus, the optimization models focus more on AUROC and less on compatibility. So when alpha is 1, there is no weight placed on rank-based compatibility, and we see no difference between the red and gray bars. And now we can see, well, what's going on with AUROC. So we'll walk through this from left to right. When alpha is 0, the focus is on compatibility. Thus, the purple bar is similar, has a smaller AUROC than the gray bar. You can see that on the far left. As alpha increases, we tend to focus more on AUROC, and we see an increasing trend corresponding with increasing alphas. We see that there's a little difference in terms of the red and gray bar in terms of AUROC, which makes sense from the definition of the loss function. Altogether, as alpha increases, CR decreases, and AUROC increases. This makes sense because the measure is putting more weight on it. Ultimately, there's a trade-off behavior between compatibility and discriminative performance. So to summarize, we think about, do we get rank-based compatibility for free when we update models targeting AUROC? From those graphs that I showed, it's a no with a caveat. If you look at the paper, there's actually a regime for certain levels of alpha that it's actually, you won't get a statistically significant decrease in AUROC, but you will get a statistically significant increase in compatibility, but it's only a sort of subset of model updating and alphas that you're interested in. Can we make updated models with higher levels of rank-based compatibility? That's yes from these experiments. If you use the new loss function or the weighted loss function with the weight mostly on compatibility, and then are we having this payoff or cost in terms of AUROC? Yes, if you're putting a lot of emphasis on compatibility. And you may be interested in doing that because you might be in a situation like healthcare where it's really important to maintain compatibility when you update a model. And so you want to think about what's the performance. Is it the team performance or the model performance? Yeah?
So for what type of underlying model is this? Do those conclusions change if I use an attention model versus a random forest?
So these experiments are specifically for a logistic regression model. I think it will change depending on model architecture. And that's one of the limitations of this work, is that you can't actually have any theoretical sort of guarantees about this. It sort of depends very heavily on your architecture. And depending on your architecture, you can be clever and start with original model as sort of a pre-training seed. And I've seen that in some experiments that we've done, if you start with the original model as the base for your updated model, you'll end up in a place with better compatibility. But it's very dependent on architecture and initialization and some of the other assumptions that you're sort of putting in your model development as well. So yeah, you may be saying, well, why would we do this trade-off? And it may just be that you're in a situation like healthcare where it makes a lot of sense to say, I'm okay with a 0.01 decrease in my AUROC as long as my users aren't going to be shocked with the rank-based ordering of the model outputs. And you can think about, well, why is that? Because your team performance here affects physician users, right? And thus it impacts patient lives. So it may ultimately be okay to do that performance payoff and a little bit of performance, give that up to have a better model team performance. So altogether, this work starts to enable developers to find desirable updated risk stratification models. We can assess updated models using this rank-based compatibility measure. Additionally, we introduce different ways to characterize it and to update the model using our measure. And well, we don't get into this at all, but there's in the paper, there's some additional sort of case study and real-world discussion with this work as well. So shifting for the last little bit into some future directions. I think we stand at a very interesting time in terms of healthcare AI. if you think about most academic medical centers right now, we have a small handful of models that are made and implemented. And ideally, we'd be going from this small handful to hundreds or if not thousands of models integrated into clinical practice in the next couple of years. And so we need to think about how do we rapidly develop new healthcare AI systems? How do we validate that these models, when we start to use them in practice, how do we validate that they're working in real time? How do we update them through the interaction with physicians? And then how do we ensure that physicians have good understanding of the models that they're using, because they're not going to be able to be trained on each one of the models that they're seeing. And so, just to prime you guys' ideas on it, I was confronted by a transplant surgeon one day when we were talking about patients, and he's like, I want to know what's the probability that my liver transplant has this like heparin-induced thrombocytopenia, or this disease that can occur when I give them a blood thinner in the hospital, and it's very potentially very devastating if we miss it. But I've missed it multiple times on patients. Like, why can't my medical record just tell me like if the patient has this risk or not? And because the existing system that we have would mean that he would need to go talk with engineers and have to spend months developing a model. They'd have to collect data, they'd have to validate it, they'd have to go implement it. And then they'd have a model that they could go and use, but this would be potentially a year or two down the line from when the initial question was posed. And from my own anecdotal experiences from models that I've made and implemented, right, these are sort of estimates of person months in terms of the time just to develop these different models. They're all sort of on the scale of months. Even the shortest one was 3 months, and this one was a sort of a COVID-related, very urgent model that was very well resourced. It still took us 3 person months to get that model together. And you think about if we're going to a place where we need thousands of models, we're not going to have that kind of lead time. So we need new methods to speed up model development. And you can think about, just as we have language foundation models, do we have medical foundation models that take in all of the different data that we have in the electronic medical record and build a bigger model that maps between the different features that we have and outcomes that we may be interested in, and then we can use that as a foundation to build other models. So when a surgeon comes and says, what's the probability that my liver transplant catheter or my liver transplant patient has hit, he can just approach a computer and have a model automatically generated for him. I'm going to skip over this last bit a little bit and sort of summarize. So we talked about 3 projects. The last one that we just talked about was developing rank-based compatibility measure and optimization for model updating. The second one that we talked about was looking about different ways that models, when implemented, may experience performance degradation and introducing an infrastructure shift and sort of bringing that to light in the field. And then the first one was looking at how to build a longitudinal model and showing its value compared to existing models. And I've done a bunch of other work, a bunch of other model implementation and development that I won't go into here, but very happy to talk about offline. And I'll just sort of leave you with the sort of fundamental ideas from this work, which is that time plays a very crucial role in healthcare. And so model developers need to acknowledge this and make it a core part of how they do model development and implementation. We can use the longitudinal information to our advantage in the case of development, and we may be able to mitigate its impact as we implement models. So if we focus on this longitudinal nature and we understand the underlying structure of medicine, we may actually be able to develop better models for use in practice. And we may be able to also advance the practice of artificial intelligence as well. And so I hope that exploring these problems of healthcare and AI, I may be able to fundamentally expand our knowledge of both artificial intelligence and create impactful solutions to improve human health. So I'd like to end and say thank you. And on Wisconsin.
Okay, so we have some time for questions. Any questions?
Yeah, Erkin, very nice talk. Yeah,
Thank you.
Yeah, the graphics is excellent. Yeah, so I have a question regarding your second project. Is when you look at the difference in the AUC.
Yeah.
So have you looked at the statistical significance of the difference? Is that difference statistically significant?
Yeah. So for that project, there when we did the bootstrap statistical significance, there wasn't a big statistical significance. There's a difference in terms of the performance overall, but when you decompose them, there's not enough to say that it's statistically significant. And it's a little bit unsatisfying because you ideally would have the statistical significance, right, in addition to the clinical significance. But when you start to dig into it, you realize that the debugging methods that we use to identify which of the features are contributing to the infrastructure difference, they actually make a big clinical difference. So it's, for example, it pointed out that the model was using ordered medicines, and ordered medicines are interesting because you would think as an engineer, oh, that's the medicine that the physician said that they wanted to be given to the patient and actually got given to the patient. But ordered medicine actually is a dynamic variable and may be updated by pharmacy. And so what you need to look at is the administered medicines, because that's actually the medicines that are given to the patient, and those are not dynamic. They are static. That's actually what goes into the human body. And so what we found was that there's a whole bunch of clinically significant findings from doing this analysis where we're like, oh, we would actually change the model because it changes the way it works. But when you look at the top line statistical significance for the difference between the two different shifts, we don't see that borne out by statistical significance. What needs to be done is we need to replicate this across other models and infrastructures and see if it's borne out there as well.
Okay, so can you give us some example about the influence of infrastructure change on the data set?
Yeah. So one of the classic ones that I alluded to was a little bit with this medications. So the way that we had made the model initially was we were interested in seeing what medications patients were getting. And what we looked at was we were looking at the ordered medications that the physician had ordered. However, there's a workflow that it goes order, review by pharmacy, and then actual administration. And in that first step, the pharmacy will very often, to me, will say, hey, did you actually mean to order that medicine? If so, like maybe consider these things. Maybe you shouldn't have done that dose, or you should do this dose, and then it gets changed. And if you take that first pit, if you take the ordered medicine, it's going to be changing, and it's dynamic in the electronic medical record. However, if you take the administered medicines, that's not dynamic. There's a couple others with the documentation that the nurses do. So nurses will batch all of their documentation, and they will say, well, at 12:30, I observed these vitals, and they write it down on a piece of paper. And then they go and do vitals for all of their patients, and then they come back 2 hours later, and then they backdate. They say vitals at 12:30 were this, but it's 2:30 at the time of entry. So if you don't look carefully or understand that your system actually gives you backdated information, when your model's expecting vitals from the development process, you would say, I had these vitals at this time, it would be okay to run the model. But when you go and do it prospectively, you would say, I don't actually have vitals at 12:30 because the nurse has yet to actually introduce them into the system.
Okay, any other questions? I have a question, since nobody has any. So this is for the CDIF prediction,
yes.
And I assume you are using vitals and labs and demographics for predicting who has the hospital-acquired CDIF, right?
So yeah.
And because your timeline is like 2019, 2020, I mean, how did you ensure that the infrastructure is not because of the COVID? Because at least in our hospital, CDIF dynamics change completely.
100%.
So how did you control for that?
Yeah, so we don't have the full, I wonder if I have it. Let me see if I have the full graphic in my appendix.